All righty. Good morning, everyone. Coming up right on 11 o'clock sharp here. So we're going to get started. For our next Eastern Region Science Sharing webinar series this morning. Couple of housekeeping notes before we get started. Number one, this webinar is being recorded via Google Meet. So per Google NOAA policy, if you're not speaking during the course of the webinar, please keep your cameras off and microphones muted. We'll certainly have time for a Q&A at the conclusion of both Dr. Schumacher and Dr. Hill's presentations this morning. If there's any other technical things, we'll tackle them as they come along. But for the time being, we're going to get started and introduce our speakers. So again, the title of the presentation this morning is Machine Learning for Operational Weather Forecasting. First off, we have Dr. Russ Schumacher. He is a professor in the Department of Atmospheric Science at Colorado State University and also serves as the Colorado State climatologist and director of the Colorado Climate Center. He received his master's in 2003 and PhD in 2008 from the Department of Atmospheric Science at Colorado State University. Dr. Schumacher's research group uses a variety of observations, numerical models, and machine learning methods to advance the understanding and prediction of high-impact weather. He received the Clarence Leroy Messenger Early Career Research Award from the American Meteorological Society in 2021. Second, pleased to have Dr. Aaron Hill. He is an assistant professor at the University of Oklahoma in the School of Meteorology. His research specializes in the prediction of high-impact weather hazards, as well as the application of artificial intelligence and machine learning in the development of prediction systems. Dr. Hill also serves as associated editor for 3 AMS journals, including the recently created AI for the Earth System Journal, and serves as a co-chair for the upcoming AI conference at the AMS annual meeting to be held in Baltimore, Maryland. So on that note, Dr. Hill, Dr. Schumacher, thank you both for taking the time to be with us this morning. And you have the floor. Welcome to the Eastern Region Science Sharing webinar series.
Thanks, Jordan. Hi, everyone. Looking forward to chatting with you about machine learning for operations and how we can leverage these new tools for your purposes. So I'd like to also note that this work is being supported by NOAA and their Joint Technology Transfer Initiative program, which primary kind of emphasis is translating these tools and products to operations to help with NWS operations. So I wanted to start off with a kind of a big picture overview of what machine learning is and what AI is in kind of the broader scheme of things. So I like to stick to this graphic where we have kind of AI as this broader circle, and even within a broader circle of applied statistics, we have these tools that in some sense kind of mimic how humans behave and how we think. That's kind of this kind of broader circle of artificial intelligence. But within that are these other subset techniques, machine learning, using statistical methods to essentially improve predictions, allowing machines to learn about events and learn about processes through iterative algorithms. And then even within this machine learning kind of circle is another subset of techniques called deep learning. We don't have to get into this too much, but it's essentially allowing the computer to use even more power and even more sophisticated computer science techniques to do image processing and similar techniques to get at what features might be in images that relate to something that you're trying to predict. For instance, if you want to predict whether an image has a cat in it, a deep learning architecture might look for whiskers or might look for ears. And it can do that in very sophisticated ways. And even kind of on the periphery is this kind of circle of data science. So all these things are very interrelated, but they do have kind of unique definitions and aspects to how we want to predict the weather as well. So why bother with machine learning? We have pretty good numerical weather prediction tools. We have good observational data sets, but in some sense, there's always opportunities to do something better. And that's kind of the first bullet point there. We don't explicitly forecast convection hazards from NWP models. So we can use machine learning, we can use AI techniques to actually make those explicit forecasts. And I'll have an example a little bit later about how we're doing that too. You might want to try to speed up something in the numerical weather prediction system. Radiation code is a good example. We know how radiation interacts with the atmosphere, and we know the mechanics of that. We know the physics, but we can use machine learning to actually speed up that process, and it does pretty significantly. And then kind of this third bullet point, we might look to try something new. We might try to learn something new about our atmosphere. This is done a little bit more in the climate sphere versus the kind of weather prediction sphere, but you might be looking for nonlinear relationships or relationships you assume that were linear, and machine learning can help you see different facets of whatever phenomena you're trying to predict. So that's kind of the reason why we're choosing machine learning and why it has some advantages. And you've probably heard this idea that machine learning is this black box, and I would hopefully will impress upon you today that's not necessarily true anymore. It's not this black box idea. We actually know what's going on within that box. It's both configurable within the code data sets or databases we use, but it's also interpretable. And that's something that Russ's student, Ali, is working on. And there's a couple of papers in the literature that have been published in the last few years that hopefully can show how we can interpret these types of models too. So where would we start if we wanted to use machine learning? We really just have to ask ourselves a handful of questions. What is it that you want to predict? Is it the probability of an event? Is the magnitude of some hazard? Do you want to predict how many lightning flashes are in a grid box? Do you want to predict the amount of those lightning flashes, or do you want to just predict whether it's going to happen or not, like a classification of a yes, no? And then you just have to choose the data that you want to input into your model. Maybe that's model data, maybe it's satellite radar, some kind of feature from an image. And then you just have to choose your machine learning model. And thankfully, what we have nowadays are these computers that are really handy at taking all of these data sources, as long as they're configured in the right way, and giving you the right prediction. So we can bring to the table our meteorological knowledge about hazard prediction and develop these really sophisticated tools. I'm not going to go too far in depth here. There's a great paper by Randy Chase from this past year that would be really applicable for operational meteorologists about these various techniques, even going back to really simple statistical techniques like linear and logistic regression that kind of show the strengths and weaknesses. So I really encourage you to take a look at that paper. It would be useful for many people in operations. But as a really kind of basic primer to how these things work, I just wanted to introduce two specific machine learning architectures, neural networks and random forests. Neural networks are these kind of interconnected inputs to neurons to outputs architectures. And there's an example here on the left. And you can think of this really simply, if you wanted to, as your very basic linear regression, y equals mx plus b. And then you can expand about how many y's you want, and you can expand about how many x's you want, which would be your inputs. And all the neural network is doing is trying to tune how those y's and x's are related to one another via weights. And so as you give more examples of hazards that have occurred in the past to these neural networks, those weights are tuned and iterated upon to essentially maximize some kind of loss function, root mean squared error or something like that. And so you can add complexity to these models by adding tons and tons of neurons. You can add what's called hidden layers, so more layers of these neurons here on the left. And you can make it really complicated if you have a really complicated problem, but it could also be made really simple to accomplish whatever task that you're trying to do. And if you've heard of convolutional neural networks, it's essentially tagging on processing to this process first, and then having some of these neural networks tagged on at the end. But in some sense, it's essentially allowing you to process an image first before it goes through a neural network. I really just wanted to provide this really basic primer where what we have used in the past at Colorado State and now here as I've transitioned to OU are random forests. And I actually think these are a little bit more applicable to understanding and how we process information. So you might imagine a forecast point like up here in the top right, and you might want to know what the probability of hail is going to be at that spot. And so you would look at the environment around that. You might look at the temperature and see if it's greater than 20 degrees Celsius. You might look at the Cape, see if it's greater than 500 joules per kilogram, etc. Various questions about the atmosphere that you could ask, and the answers to those allow you to traverse a specific tree, and then you can get an answer at each of those trees. So the aggregate prediction across all of these trees within the forest gives you a probability of, for instance, in this example, severe hail. And so it allows us to make predictions across an entire grid and essentially arrive at a forecast across the entire U.S. Russ, do you want to take it from here?
I can take it from here. So that hopefully gives some good background into a little bit about how these work, and then now we'll transition into some of the specific applications that are going on now, including our work and some other work that's going on out there. And I think you can classify these approaches, at least as they're being used right now, into two overarching classes. So the first one is for post-processing, and that's what we've done in our group, is basically taking NWP model output that can't specifically predict a thing that you want to predict, like severe weather or excessive rainfall, and use the machine learning to identify the relationships in the data to basically either give you better calibrated probabilities, or do bias correction, or like Aaron said, do something better that you can't do specifically with the NWP models. This category is much more mature. There are things being used in operations and being transitioned into operations now, and a lot of that uses maybe the more traditional ML techniques like random forests, and so on. The second piece, which we'll come back to a little bit later, is the much newer field of doing data-driven weather prediction. And so this is basically using machine learning to do the same things that you do with an NWP model to predict the entire state of the atmosphere. This field is really new, and it's evolving really rapidly. Had Aaron and I given this talk 6 months ago, we might not have even talked about this because it was like so new at that point. And today we can tell you quite a bit more. And I bet in 3 more months, there's going to be new results and new ways of thinking about this. So it's evolving really quickly, but it's still really new, meaning that there hasn't been all that much testing in operations or kind of in real operational settings, but now that's starting to happen, and we'll touch on that a bit later. All right, go to the next one. All right, so we'll talk a bit about what our system that hopefully you might be familiar with, that we refer to as the Colorado State University Machine Learning Probabilities, or CSU MLP system. So since about 2016 or 17, we have worked with the operational forecast centers, first with WPC and then more recently with SPC, to develop this basically first guess guidance. That was something that was seen as a gap at both operational centers, basically a starting point for forecasters when they're drawing the excessive rainfall outlook at WPC or the convective outlooks at SPC. So you can see on the bottom, this is from Tropical Storm Ida in 2021, the operational tornado outlook and ERO from WPC there. And then on the top are our products, the day 2 outlooks for that same period, and so we present them to kind of make them look similar to the operational outlooks, and that makes it easy to do sort of a comparison for both for us and for the forecasters when they're looking at that. So there's, if you're not familiar with the real-time forecast, the link is there. We'll show that again at the end. And then there's a few papers over the last few years that have kind of described the severe weather models and the excessive rainfall models. Go to the next slide, Aaron. So there's just zooming in on that Ida case. Had we had a little bit more time, we'll draw one of these up for the event that happened over the weekend there in your backyard. But you can see this was the day 2 excessive rainfall probability zoomed in over the Northeast. And with the probability categories that align, or at least did kind of align at the time with the WPC probability categories. And then on the right is the blue and yellowish dots are the observations of excessive rainfall in that case. And you can see in that case, it's, certainly there's some you can quibble with some of the details, but it did quite a good job in that one. Go to the next one. This is an example from the severe weather model. This is another one of the kind of success stories, I think, from this system. This was the big severe weather outbreak that happened in the Midwest in mid-December of 2021. Really unusual event, in terms of the time of year. It was the most tornadoes on a single day in history of Iowa. And our system was picking up on it, day 7 and 8. That's showing, like the 5% probability contours. There's at least a hint of something there on day 7 and 8, especially as you get to like day 6, 5, 4, and 3. And then as the event approached even closer, it's locking in on probabilities in the areas where the severe weather ended up happening. It's fairly confident, or fairly high probabilities. It's not jumping all over the place. So these are characteristics that are good to see. Of course, not every forecast is as good as this one, but it shows the potential for this sort of thing. Next slide. And if we do look at the statistics, so now kind of looking at an aggregation of skill from, so this is for the excessive rainfall model, and so I won't get too much into the details, but we're verifying it against WPC's Unified Flood Verification System. And these are two different versions of the model, which are, if anybody's interested, we can kind of explain the differences between them. But you can see the results are pretty similar between the two models. But what's shown here then is Breyer skill score with respect to a smooth daily climatology. So higher scores are better. You see skill decreases with increasing lead time, as you kind of expect with any forecast. But you see that there's positive skill, better than climatology, all the way out to day 7, at least a little bit, certainly at day 6. And this has been a helpful tool for WPC as they extended the ERO out to 5 days, and might consider extending it out further in the future. It's helpful to see, kind of where are we at this point in terms of these predictions. And if you look at this in the severe weather model, actually the skill is even higher out at these longer lead times there. So it's kind of showing the quality of the forecast that you can get out of these forecast systems. So next slide. And this is kind of another interesting way to look at this. These are so the forecasters at SPC basically were given a big set of our CSU forecasts versus the operational, to compare them to the operational SPC outlook, and to give subjective ratings to them. And so what you see here, so the colors of the bars go from basically day 1 in orange to day 8 in the greens, and they were asked to rate them, much worse, slightly worse, about same, slightly better, much better. And what's kind of interesting that pops out here, and we see this in the quantitative numbers as well, is that around day 3 and 4 is where you see more ratings of better, slightly better, or much better, compared to the operational SPC outlook. So this is kind of what we've found over time. It's really, really hard to beat expert human forecasters on day 1. You all are experts at synthesizing all the information, the observations, all the different models, all the different data that's out there to make forecasts. And so generally the human outlooks perform better than machine learning at day 1, and to some extent we see that here at day 2. But then when you get out to like day 3, 4, 5, that's where the relative value of the machine learning really seems to shine, because that's a time period where you don't have as much guidance as forecasters. It's harder to connect the current observations to what's going to happen out at 3 or 4 days from now, and the ability to process decades worth of data to make a well calibrated probability really starts to come in there. And then you get out to like days 7 and 8, and it's just hard to make a good forecast no matter what you're using at those time frames. So next slide. So one of the things we've been working on lately that I think is kind of exciting from a connection to operations perspective, right? So Aaron talked about the idea of the black box earlier, that you sort of throw some data in and you get an answer out and you don't know what's going on in the middle. But we actually can learn that now. And so this is an example from Ali Mazurek, a PhD student in our group here. Using a tool called Tree Interpreter, and it basically takes those random forests and picks apart all those decision trees to figure out what variables that machine learning model is using, not just in aggregate, but at a specific time and a specific place in a given forecast. So this is one single time from a day 3, so it's a 21Z on this day back in May of 2022 in the day 3 outlook, and it shows which of the variables are increasing the probabilities in red or decreasing the probabilities in green. And it turns out that the machine learning system, I mean, I think we can interpret this in the sense of we all use ingredients-based forecasting. That's how we're all trained to forecast severe weather. And machine learning seems to be kind of figuring that out. So you can see, for example, CAPE is almost always one of the variables that increases probabilities. Precipitable water, if you look at the low-level shear in the lower left, that's the surface to 850 millibar shear. So those are all the things we would, probably think about if we're forecasting an event. And then you can also see, for example, like the precipitation field from the GEFs is reducing the probabilities. The SIN in some spots is reducing it, and some other, interesting patterns in there. But that's kind of a vision we have, is that as forecasters would be able to look at this in the same way that you might look at ingredients from some, the GFS or the GEFs or the European Center model or whatever, to kind of connect the ingredients-based thinking to what the machine learning is showing. So next slide. So there's a few other examples out there that are happening either in operations or applicable to operations that you might be familiar with or at least aware of. So NCAR has been running neural networks applied to the HER. And you can kind of see, the loop there that's showing the loop of probabilities of severe weather there. You may have seen NATOcast, which has mostly been on mostly seen on social media, but it's quite a good forecast tool as well that uses a method called gradient boosted decision trees. So not too different in principle from what we're doing with the random forest, but a little bit of a different method. Next slide. This is kind of a cool one. This is a group at OU that's doing using machine learning to do objective analysis of fronts, right? So everybody's kind of struggles with where do you draw the front, and can you derive it objectively from whatever data set you have. They've applied deep learning to and worked closely with the WPC to kind of produce these depictions of fronts operationally that can assist the forecaster when they're tasked with putting the fronts on the map and the surface analysis. Next slide. And then this is kind of a cool application of a group at CIRA here at CSU, basically taking I think the product's called Gremlin, and the kind of idea is you estimate you make some estimation using machine learning of latent heating from radar data, and then you can assimilate that into a model, for example, like the HER or the RRFS. Or they've also used this kind of method to basically create synthetic radar data in places that you don't have radar. So you take satellite information and kind of connect it to radar in places you do have it, and then you can kind of move that to some place where you don't have radar data, like over the ocean or over some other location, and generate it that way. So this is another pretty cool technique. Next slide, and I'll turn it back over to you, Aaron, for this.
Thanks, Russ. So yeah, Russ highlighted this data-driven weather forecasting idea, which has garnered quite a bit of press over the last few months. Specifically, a article put out by the European Center that essentially noted that these ML models are becoming competitive with NWP models, which created quite a stir. And there's three primary systems that are now out there, some of them publicly available, others not. You can see the systems there, one by Google, another by NVIDIA, and then a third by Huawei called Pangu Weather. And the idea behind these is that they are trained on reanalysis data sets, and then they can be run in real time using the operational initial conditions from, for example, the European Center models. And one of the benefits of these systems is that they can run at lightning fast speeds compared to our operational models, where we can generate thousands of ensemble members in a matter of just a few minutes, which you can imagine the operational benefits to something like that. Let's see. So I'll kind of run through these examples to kind of show you where we're at in this field, and kind of where we're headed as a collective. So this new Pangu weather model is actually being run experimentally now at the European Center. And the article in Nature that was published this last year describes the system, but operationally, it's actually running off the European Center's 40VAR analyses. So they can run it in real time as a deterministic system alongside the European Center model, which is, to me, just fascinating that they're able to do this in a really short amount of time. Now, at the moment, it's just a deterministic model system with standard synoptic fields. You can take that for what it's worth. But they are publishing that, and it's now available online. If you search Google, you can find some of these fields. And I provided an example there on the right of just the 500 millibar heights and 850 temperatures from a few months ago, or about a month ago. You might think, if you didn't know that was a machine learning model, that came from a dynamic system. So they're starting to produce forecasts and products that look very, very similar to what we as forecasters are familiar with. A lot of this work, though, was pioneered out of the University of Washington and Dale Duran's group, and Jonathan Venn was a grad student there. They developed these algorithms that essentially intelligently time step so that you can create these multi-day forecasts from these systems. So on the left is a machine learning model, and on the right is they're verifying synoptic patterns. Really, this just proves more evidence that these multivariable models can actually produce realistic weather, tropical cyclones, mid-latitude cyclones, and features that we would be familiar with as meteorologists. And this is the third example that I wanted to show. This is developed by Google, which is a 90-minute nowcast of rainfall. One of the caveats I've heard from these models from the community, and myself included, is that, well, they're not producing realistic rainfall signatures at the synoptic scale. So there is some hesitation with how much we can use them. But there are some other systems that are actually producing rainfall from these machine learning models. So the top left of this GIF image is the true rainfall. And then you have a variety of different machine learning architectures that are producing rainfall over the next 90 minutes. You can kind of get some blurry representation depending on what machine learning model you use. But this generative AI field that we're now kind of diving deep into as a community is producing some really realistic rainfall depictions. So there is some hope that these types of systems can provide a lot of utility in the near future. So just quick few takeaways from the kind of data-driven weather forecasting side. While these techniques are getting a lot of press and they're making a lot of waves, they are still kind of at an infancy toddler stage of development. Even the fact that they're running experimentally operational centers, we don't know exactly what utility that they will have quite yet. And I say that a week after a very good paper was published by another researcher at the University of Washington, essentially showing that these systems are behaving in a dynamically and physically sensible way. So potentially in the next 3 to 6 months, all of what I'm about to say is a moot point. But at this point, there's really early stages to where data-driven weather forecasting is and where it's going to go. However, the kind of pros of these systems, as I mentioned before, you can create really large ensembles, and the skill of these systems is competitive at a large scale with the dynamical system or dynamical models that are running operationally already, out pretty far as well. Some of the cons, however, is that they do still rely on the NWP models, and maybe they always will. Maybe they will have to. But one of the things that the European Center is doing is actually leveraging these data-driven forecasting models to then improve upon their physical models, what they call hybrid modeling, essentially allowing the physics models to drive the data-driven models and then allow the data-driven models to inform how the physical model should be improved. But as I mentioned, there's still some doubts about whether we can generate storms or precipitation at convection scales. That's obviously very, very important for operational forecasting here in the US. Can we create those forecasts at day or two ahead lead times? I don't know yet. And that's probably where the next revolution will have to be related to these systems. So just a quick summary here. The advance of AI and machine learning is really advancing rapidly, from the post-processing tools that Russ alluded to these data-driven models. But all that to say that there are really useful tools out there, including our own products, that would be really useful for operations. But they are just tools. They're not the end-all be-all. And you'll want to definitely stay informed on how this development is happening. I encourage you, if you are at the AMS meeting this January in Baltimore, please do come to the AI conference. We will have a number of sessions related to data-driven forecasting and research operational tools as well. And I'll end with this final point. The best outcome that we can have right now is if the humans, the forecasters, the numerical models, and the AI predictions all kind of complement each other with individual strengths rather than competing with each other and trying to figure out who's going to replace who. So with that, the forecast products that we're producing in real time, you can use that QR code or our website URL there. And feel free to reach out to Russ or I if you have questions or comments afterwards. Thanks so much.
All right, Russ, Aaron, thank you so much, first off, for presenting not just the Eastern Region folks, but people across the agency on this call right now. So much really important, relevant, and really insightful information and points being made here this morning. Before I throw any thoughts of mine onto the floor, I wanted to ask anyone across the field virtually if there are any questions out there or thoughts. Frank, please go ahead.
Yeah, great stuff, gentlemen. I'm trying to, as a SUE, that's my job. I'm trying to answer a lot of questions, frankly, because there's an awful lot that's being sent down from the top on information about AI. All you got to do is look at social media to see anybody who's following weather Twitter, if you will, or weather X, I guess it would be called now, or whatever. Keep seeing things like these NATO casts. I know in our office, we're big users of the ML stuff that you guys send out as part of our daily look at both the threat for severe weather and for heavy rainfall. But my question is, we see these things like we have the European site has, the Pangu, and it's got the DeepMind, and it's got the Hawaii, or however you say it. It's got the different ones on there, but it's really, and you mentioned this in your discussion, it's really still, there's not all right, there's a hurricane. I'm seeing it go, but there's no detail. When do we think that we'll start to get some more experimental information out so that we can actually look at it? Because right now it's kind of, from an operational perspective, it's kind of interesting, but what we have is a lot better now. So, and I know that this is a tough question, but what are the timeframes where we can start introducing some real stuff that we can work with from an operational perspective?
That is a great question. I have been surprised by how quickly this kind of subfield has been moving. I would not be completely surprised if within the next year there was something that could be used. I don't know what form that would take. If we're specifically talking about like these 3 or 4 data-driven models. But I will mention, like, Pengu is open sourced on GitHub. Anybody could technically run that model right now. And yeah, so in some sense, I think it would take just a very quick researcher to kind of make a system that could be applied regionally, that could be applied for a specific phenomenon. And I don't know exactly how the model works there kind of to run locally, but I would not be surprised within the next year, maybe two, that something could be useful for operations. Rusty, I don't know if you have any thoughts on that.
A quick researcher with a big computer.
Yeah.
Because that's some of the issue here is that these are all being developed, at least the ones that have come out so fast have all been developed in the private sector. And the code's open source, like Aaron mentioned, so it is, I mean, that's a really great benefit. But it's also difficult for whatever, for universities or for maybe even government agencies to acquire these big GPU systems that you need to run these, because it's a different computing framework than what we are used to using in our field, which is lots and lots of CPUs distributed to make NWP models run fast. And these GPUs is just a different computer architecture that those are expensive and all that. So I think that's going to be the interesting thing to see how it plays out, is how much of this information that's out there is sort of made publicly available versus what is happening in-house at these companies, or whether the European Center, for example, or some university or some group within NOAA can spin them up and get get output that's sort of out there and available for everyone. I think it also really remains to be seen. I mean, I don't think anyone has very successfully done the weather that people care about yet with these, like precipitation. I mean, nowcasting, yes, but like not the 3-day precipitation forecast. Those at this point are the bit of results is out there. They're not very good compared to the NWP models. But I think that's just a matter of time. They figure out how to, because precipitation's a harder variable to forecast, as we all know, than 500 millibar height. But I think it'll probably get there before too long, because surely these groups are know about that and are working on it.
Yeah, thanks, gentlemen. Obviously, it sounds exciting, but
Yep.
I want to see some results before, and I got to think that anybody who's going to spend a lot of money on a system to run something like this would also like to see some results before they make that kind of investment.
Yep. No, absolutely. And I mean, I've kind of been thinking about this too. I mean, maybe the end point for all this is not that the forecasts are any better. They just run 1,000 times faster. And that's a benefit too, if that's, even if that's the only place that it gets to. But yeah, remains to be seen, especially for the impacts and for storms and things like that, where it hasn't really been tested, or at least not demonstrated much yet.
Well, thank you, gentlemen.
All right. Thank you, Frank, for that very good question. Are there any other questions? Okay. Andy, please go ahead.
Yes, thanks for that great talk, Aaron and Russ. And you presented some similar material, but I was obviously having to keep updating it with the speed of AI and ML stuff. So I had a quick question. If you had a best recommended intro to AI ML, I mean, it could be in me logical space, and I know you had to just do a quick gloss over of how that works. What would be your best recommendation? I know Jeff shared a couple of good papers in here, but for those that may just want a nice video-ish type tutorial, or is there, I don't know how much, I mean, obviously this stuff's, I bet some of the stuff is advancing so fast that even the underlying documentation is having a hard time keeping up.
Yeah, I don't know, Aaron. Do you know of any like videos or like? I mean, so that the part 1 Chase et al. Paper, I think, is a great one, because it walks through, right from the start of linear regression, which everybody kind of already knows how to do. You certainly learned that in Excel in some class, down to some of the other ones. And what's also nice about that is if you want to, it comes with code basically and data that you can just pull and kind of walk through the examples yourself. I mean, there's tons of general stuff online on videos, YouTube videos, or tons of websites about the basics of ML in general, not specific to meteorology. I don't know, Aaron, have you found anything kind of good on that out there? Does AI2ES have anything like that?
Not that I know of. And if they don't, I think I'm probably going to recommend that we create something like that. It's a great idea. Most of what I learned 4 years ago when venturing into this was a website called Towards Data Science, but it's, as Russ alluded to, it's general. Their examples might be like predicting home prices. And they walk you through like a number of different types of algorithms, but it's not unique to meteorology. That being said, Randy's papers are great. And I think that maybe there's an opportunity here to actually create some materials. I think that's a great idea and something that I'm going to think about a little bit more seriously.
Yeah,
and I'll
thanks.
put here
It'd be good for those that are like maybe really wanting to get started into this field, and get them into it. Yeah, and I mean, myself personally, I would love to. I was actually speaking to my boss Randy about it last week. I'm just like, I'm spread thin through a lot of different areas. So I was kind of curious about that. Thank you very much.
Yeah, I just threw one in the chat that it is at least a meteorological application, and I think it's a really nice introduction to like just if we're for a random forest specifically to like how it works. It's sort of a contrived example. It's like, okay, you have a time series of precipitation at a location. I'm going to train a random forest to predict the high temperature tomorrow based just on the history, the history of temperature there, which, as you'd expect, doesn't do all that well, but it does, it kind of shows you how the system works, and it at least is a it was helpful for me because it's the variables at least are intuitive, because it's okay, how would I go about predicting tomorrow's temperature if all I knew was yesterday's temperature and the history of temperature at some location and whatnot. So it's maybe a helpful one to walk through. And there's lots of other examples kind of like this. I mean, this requires you to code a little bit, but not all that much.
Andy, thank you for that great question. Actually, not to steal the thunder, I was actually going to ask the exact thoughts. But one thing I was going to mention is the link that was shared, the Towards Data Science. We can also link that with the recording once we have it available and get it up, so we have an initial starting point, because I think that is a really great point for especially the forecasters at offices across the entire agency to get their feet wet and understanding the big point about what you actually said in your presentation, the last bullet point, where how to leverage it as opposed to feel like it's a competitive force in the forecast process. And thank you. Yeah, Jarrett, thank you for that comment as well about the Rober lectures. We actually have that linked as well. Jeff, please go ahead.
Yeah, I'd like to mention two other kind of newish activities. One is new AMS journal, AIES, Artificial Intelligence for the Earth Systems, that kind of really only started in early 2021, but has really kind of taken off as a place to publish relevant papers on AI techniques. And then the other is AI2ES. This is an NSF-funded institute for research on trustworthy AI in weather, climate, and coastal oceanography. And it's a consortium of a number of universities and some private entities as well, to really kind of help dig into the methods that are using an AI and ensure that what's going on in some of these blackish boxes really is utilizing top flight and reputable approaches. So, and they're doing some really good work in that area as well. So it's really kind of a community effort that I think is kind of pretty exciting to kind of not go into this, blindly, but really responsibly as a way of advancing the science.
Yeah, I think that's a really good point, Jeff, and it's I think we'll see it similar to any other research in our field, right? Like the kind of tension between the shiny new research and then making it actually applicable to operations. And I think we've even seen that in the work that Aaron and I have done here and others. We've put a high priority on, and it's partly because of how we were funded through JTTI. It's a high priority for them on seeing this all the way through to the operational transition. When we could have sort of stopped 2 years ago and said, all right, we kind of figured out what we can figure out with random forests. Now let's see what we can do with neural nets. Now let's see what we can do with, this other technique that just came off the shelf. And there's going to be a lot of people that do that. And I think you need people to be doing that as well. But I think it is, helpful to have this priority to actually transition it into operations, and, which takes a long time, as you all know, for lots of reasons. So the kind of the incentive for researchers or, whoever it is to kind of, cross that valley of death, as they say, it's been good from my perspective, but those kind of incentives need to be there for that as well. And the incentives are there in the private sector, because it's you develop some product that you can sell or you can make money on or whatever. Then, but in this context, the incentives are a little different, right? It's public safety and saving lives and all that, and making a better quality forecast. So that incentive needs to be there too.
All right, thank you, Jeff, and thank you, Russ, for the insights on all those points. One question I had, based on your comment in chat, Aaron, will there be any period in which there's an outage to them being transitioned, these different models, where they become open source, or no?
There shouldn't be any outage.
Not on purpose, at least.
No. We will, for now, still have them run locally at CSU. The transition is more to fulfill the JTTI contract, or whatever it is that we signed and agreed to have them run on SPC and WPC computers, to have them in-house at those operational centers, and in some sense just so that they can get the data faster for their purposes.
Yeah. Okay. Well, and we don't have 24/7 people, so I mean, there are days when ours doesn't run because whatever, some computer issue happened. Whereas when it's running on WCOS or at WPC, then there's somebody there that in principle will make sure that it runs even if there's an issue.
I am currently our IT department.
Right.
Fair enough. To the points before about the rubber lectures, and also as an FYI, to where this webinar, once it's available, will be posted. I'm sharing a link right now. That is where this webinar will be hosted, and also where we have the links as well to the rubber lectures that Jared mentioned earlier in chat. This is an FYI to everyone here. I think a big point to make here is, with as fast as AI and ML is moving forward, and with all the tools and resources mentioned today, some of which many of you and staff at our various offices and regions are already familiar with, and some that we may not be, it's an opportunity to begin learning too. And this is hopefully a good opportunity and a good stepping point to learning about the machine learning that you're doing at Colorado State, to the other tools being developed elsewhere, to NATOcast and other tools. So it doesn't become an onslaught of information, but rather something we can fuse and leverage as we're moving forward, as opposed to being thrust and forced upon operations, but being able to effectively leverage and target it as a tool that we can use to support, even when there are certain models that are not completely open source and data that's evolving as fast as you both have highlighted this morning, and in ways we probably can't predict even right now where we'll be in 3 to 6 months. So just my own 2 cents. Are there any other questions from folks in the field? Okay, it's quieting down a bit. Really, just before we get close to the top of the hour, to you, Russ and Aaron, thank you so much to both of you for speaking with us this morning. This is increasingly more relevant as the days move along, and it is a topic that is most definitely not going anywhere. It's something that we need to be continually aware of and will be. And as more and more information and more resources come out, just something that we need to stay on top of. So really, thank you so much for all this, for taking the time out of your days to present to us. And I guess if there's no further questions, the big ones I would have asked already were already presented, so I won't take any more time. Just thank you so much to everyone, for all of you in the field, for attending. And if there are any further questions beyond today, you can certainly reach out to Russ and Aaron. They seem very open to responding to things. At once this webinar is available, we'll have it available on the Eastern Region Google site. I shared in chat a few moments ago, and we will go forward from here. And one final note I will make away from today is this Thursday, just a reminder, we have our next Eastern Region Science Sharing webinar focused on Lightning Cast, coincidentally, another algorithm in this same topic of conversation. So look forward to seeing many of you there. Thank you. And I guess with that said, any final thoughts, Russ and Aaron?
No, thanks everybody.
Thanks.
Great to chat with everybody, and yeah, happy to answer questions as they come up.
Sounds good. Thank you so much. And to everyone in the field, have a great rest of your Monday.
Thanks, Jordan.
Take care. Thank you.